The Manhattan Project, the making of the atomic bombs that ended the Second World War, was an extraordinary achievement of science, math, and engineering, accomplished under exceptionally difficult conditions by some of the most brilliant minds of the 20th century. The recent film Oppenheimer barely touched on the full nature of the achievement. The topic of the making of the atomic bomb is huge, and my talk, like the recent film, can only cover selective aspects of it. My talk will have 4 sections. About a third or half will be a non-mathematical presentation of the essential physics underlying nuclear fission. I hope you find it fun to learn. It's a necessary context to understand my next set of 3 topics, which were what were the actual challenges and difficulties in creating the bombs that ended the Second World War. Throughout the talk, I'll illustrate the fundamental importance of objectivity in overcoming what seemed to be insurmountable obstacles to the creation of the bomb. I can't repeat the lecture I gave a few years ago, but in essence, a nucleus is made of protons and neutrons. Protons have positive charge, so what holds a nucleus together? If you had only 2 protons, they would fly apart because they have the same charge and they would repel each other. What holds it together is not gravity, but a third force called strong interaction, which is, unlike gravity and electromagnetism, a very short interactive type of force. You could think of it like a contact force, or more simply, you could think, this is a really simple view, the nucleus being held together by neutrons acting as a kind of glue connecting protons. It's a little bit oversimplistic, but that's one of the roles the neutron plays. The entity whose nature and action will dominate everything I discussed today is the neutron. The first action of the neutron we will be looking into is its action in initiating nuclear fission. So the neutron was discovered in 1932, and nuclear fission was discovered just a few years later at the end of 1938. What occurs in nuclear fission is a fast neutron, or sometimes a slow neutron, depending on what material it's hitting. A neutron hits uranium and imparts energy to it. If it imparts enough energy to the uranium nucleus, the nucleus begins to wobble. The protons and neutrons are in motion. And if the wobble is big enough, the nucleus splits, creating 2 daughter nuclei and emitting some very fast neutrons. By very fast, they can be traveling at about 5% the speed of light. This whole process between the impact of the neutron and the fission occurs in less than a trillionth of a second, and it releases a relatively enormous amount of energy. What I mean by relative is relative to a chemical process. So if one had a nuclear reactor and uranium, and if all of the nuclei of the uranium could undergo fission, a kilogram of uranium would generate as much energy as burning 3.4 million kilograms of coal. You can see why, if people are worried about increasing carbon dioxide, they should all be championing nuclear reactors. If instead of releasing the energy slowly, it was in the form of a bomb, then same equation. A kilogram of uranium has the potential of explosive force equivalent to 3.4 million kilograms of TNT. News of the discovery of nuclear fission spread quickly. Physicists in the US and Europe immediately began to do experiments that replicated the original discovery of fission and began to do new experiments that expanded our knowledge of the process. Most significantly, Enrico Fermi, who recently immigrated to the US from Italy, led a team of physicists at Columbia where they performed the first nuclear physics experiment in the US and began a series of groundbreaking experiments, which we will return to. At the time nuclear fission was discovered, Niels Bohr was the leading theorist on the structure of the nucleus and its binding energy. In fact, the discovery, the interpretation of experimental results as nuclear fission rested heavily on Bohr's prior work on the liquid drop model of the nucleus. So in February 1939, just 2 months after nuclear fission was discovered, a colleague of Bohr told him about recent experiments whose results contradicted Bohr's model of the nucleus. The experiment was done by a scientist who Bohr knew and respected. So how did he react? Did he attack the experimenter or dismiss the evidence as unimportant because his theory was too beautiful? Or did he quickly abandon his theory because he believed one observation could invalidate its entire structure? He did neither. He sat silent for a long time, deep in thought, and then he explained, "Now I understand everything." And he walked to his blackboard and drew some graphs. So what was the issue and what did he explain? So on the top there, I've replicated that picture of what is involved in fission. So Bohr's theory predicted that the nucleus of ordinary thorium that has 90 protons and 142 neutrons is called thorium-232. Whenever I speak of an element and I say thorium-232, the 232 refers to the number of particles that make up the nucleus, the number of protons and neutrons in the nucleus. So Bohr's theory predicted that thorium-232 and uranium-238, the most common form of uranium, should behave the same way when hit by a neutron. Why? Because they had both an even number of protons and an even number of neutrons. You could ask me in the question period why it matters whether it's even or odd. And under this theory, there are two sources of energy when the neutron hits the nucleus. One is a binding energy. And under Bohr's model, if the number of protons and number of neutrons were even, then adding one more neutron to the nucleus would add just a little bit of binding energy, too small in itself to disturb the nucleus much, too small to cause fission. So therefore, if a slow neutron hit one of these two nuclei, you would not get fission. On the other hand, if a very fast neutron hit them, you could. Nuclei that only undergo fission when they're hit by a very fast neutron are called fissionable. And the distinction between slow neutron and fast neutron is actually enormous. It's not just a small qualitative difference. It's a differentiation that Enrico Fermi formulated in the 1930s as a result of the groundbreaking first experiments he had done bombarding nuclei with neutrons and observing what happened. And so the distinction he made is a slow neutron is one whose energy is the same kinetic energy as gas molecule at thermal temperature, whereas a fast neutron is a neutron defined as having 1 million electron volts of energy. It's the kind of energy that comes when a nuclei splits, which of course Bohr didn't know about at the time, but also the energy of a neutron that's created by radioactive decay. And the difference is really enormous. So if we only looked at the speed, the fast neutrons are traveling 10,000 times faster than slow. So this isn't a minor difference. So that's what we mean by fast and slow. They're a very big difference, and they're differentiating the different kinds of nuclei that undergo fission. So thorium and uranium-238 are fissionable. But the experiment that seemed to contradict Bohr said that, no, in uranium, slow neutrons can also induce fission. Bohr's insight that day was to remember that there, in fact, were two forms of uranium. U-238, which 99.3% of all uranium is 238, but 0.7% is an isotope that had only recently been discovered. Bohr remembered it had been discovered and that it was very rare. What we mean by 99.3 versus 0.7 is ordinary uranium is a mixture of both type of nuclei. When you have an atom, an element like uranium that has different nuclei with different number of neutrons, those are called isotopes of the element. So 238 and 235 are both uranium atoms. They have exactly the same chemical properties, but they have different nuclear properties because of the number of neutrons in the nucleus. And according to Bohr's theory, because this has an odd number of protons and an even number of neutrons, adding one neutron, no matter how slow it's going, the binding energy of that neutron was so great, it would create fission no matter how fast the neutron was moving. Now, you may say, and that kind of nuclei that can undergo fission no matter how fast the neutron is impinging on it is called fissible. Now, you might say, okay, this is really boring. Like, who cares about this? Why this was fundamentally an important insight of Bohr, profoundly important, is only fissible nuclei can undergo a chain reaction. Therefore, only a fissible nuclei can be used to make a bomb. And here's more. About a year after Bohr hypothesized this, a team under Fermi at Columbia confirmed that, in fact, Bohr was correct. What's interesting for our purposes of there are 92 naturally occurring elements in the world and 339 naturally occurring isotopes found in nature. Only one isotope, U-235, is fissible. Only one of all of the isotopes in nature is capable of undergoing, being fuel for a chain reaction. So this was a really important identification. Now, about 2 years after Bohr made this identification, another man-made isotope, plutonium-239, was found. 239 because it has 94 protons and 145 neutrons. And his theory predicted, for the same reason that U-235 is fissible, that this would be fissible, and it was confirmed. And in fact, these were the only two available fuels to make a bomb. And these were the first two major challenges in making a bomb. To give you an understanding why, when Fermi's team at Columbia confirmed that U-235 was fissible, how did they get the U-235 to do that? Well, there was a scientist I think it was in Minnesota, who had a very large mass spectrometer, which we'll talk about a little later, who ran it for several days until he accumulated enough U-235 to send to New York. And when I say accumulated enough to put in an envelope, which he sent through public mail. So we're talking about a few grains, and it took several days to just accumulate these few grains, and it was literally sent through dropped it in the mailbox, and it got sent by public mail. So you can see now there's a problem. How do you create enough, how do you separate out, atom by atom, the two isotopes to create enough material for a bomb if they have identical chemical properties and cannot be separated chemically? It took a few days to just create a few grains. How do you create enough to make a bomb? And the same thing with plutonium. It was made in an accelerator by people under Ernest Lawrence at Berkeley. And again, they had a tiny amount that they created that they could determine its properties, and they determined, yes, it is fissible. But for both sources of fuel, how do you make enough to make a bomb? So before we discuss this, let me just explain a little bit more about nuclear fission. But before I do that, let me show you, very interesting, this is something that you would think only would occur in a novel. So Bohr submitted his paper on June 28th, 1939, describing all of this, the mechanism of nuclear fission, submitted it to Physical Review, which is the leading journal in physics. Notice what I titled this, The Beginning and the Means to an End. Why was that? The paper was published September 1st, 1939. Of course, September 1st, 1939 was the day Germany invaded Poland from the east. 2 days later, Britain and France declared war on Germany, and 2 weeks later, Russia invaded Poland from the west because Hitler and Stalin had agreed to do that and divide up Poland. And so very interestingly, the very day, the action that immediately triggered the Second World War, a paper was published with the means to end the war. I thought that was an interesting poetic coincidence. Okay. Something that a novelist might do. So what is nuclear fission? You probably have all seen diagrams of a neutron hitting a nucleus, the nucleus dividing into two daughter cells, emitting some fast neutrons, and let's say two of the three strike other nuclei, and so you go from one division to two divisions to four divisions, and you have an exponential growth of doubling every stage. And that certainly is something that can happen. But I want to slow this down to make some differentiations. An important concept is criticality. It's the condition in which the number of neutrons produced at each stage is constant. It doesn't have to be just one sequence. You could have two or a billion. But this is simply to illustrate nuclear fission is in a critical state. It's reached criticality when it's in a steady state. Now, why is that important? That's necessary for a nuclear reactor. In a nuclear reactor, you don't want the energy to keep doubling every hour, every day, because it'll end up melting the reactor. Subcriticality is when the number of neutrons produced in a chain reaction are diminishing, so the chain reaction will eventually die out. That's also something you want to be able to create in a reactor to turn it off. Supercriticality is when the number of neutrons in the process grow, but they don't have to grow at the rate of doubling. They can grow like interest at 1% or 6% or 10%. So you may wonder, well, if these are all natural processes, how do we control the rate at which the nuclear fissions are occurring? How can we control a chain reaction? And it was Enrico Fermi who figured that out, and we'll talk more about that in a short while. You insert material that absorbs neutrons. And so by inserting material that absorbs neutrons, you can control the process and have it go at any rate you want. But it's important to understand those concepts. Now let's return to the standard picture of a chain reaction. This conceptually is correct. It captures the essence of what a chain reaction is, where it's doubling at every stage. But there's a distortion in what the actual physical process is, because in creating this, you've omitted some critical measurements. And let's see what consequence of reintroducing those measurements are. Particularly, when you look at this diagram, it looks as if each nucleus is about 5 radius or 5 diameters of nuclei apart. So here's a nucleus, and about 5 times that distance, there's 2 more nuclei, and about 5 times. So you might say, well, who cares? Why be picky if it's 10 times? Isn't it still a good picture? And the answer is no, for the following reason. The actual relationship between the radius of the nucleus and the radius of an atom is a nucleus has a radius about 1/10,000th of an atom. And that will be true for simple atom like hydrogen or a complex one like uranium. So if we imagine an atom had a volume of a sphere a mile in diameter. So those are 4 Empire State Buildings. That's about a mile. So imagine you have this giant sphere a mile in diameter, 2 miles high, 8 Empire State Buildings high. How big would the nucleus be if that's the size of an atom? It would be approximately the size of a basketball. So imagine a basketball on the top of the 4th Empire State Building. That's how small the nucleus is relative to the size of the atom. So if we had 2 adjacent atoms, we see immediately that the next nucleus over is not going to be nearby, it's going to be 2 miles away. You don't quite get it from that picture. But things are much more different than even I've said. Now think about what happens when a nuclear fission occurs and the neutron comes flying out. What's the likelihood it's going to hit another nucleus? Well, you have to think about this. If we thought about this purely classically, we would ask, what's the ratio of the area of a nucleus to the area of the total atom. And it would be 1 over 10,000 squared, or 1 in 100 million. So the probability of a neutron hitting another nucleus, according to this picture, would be 1 in 100 million. That would mean that the next nucleus that would be emitted if that basketball underwent fission isn't going to be close by. It's going to be 200 million miles away. 200 million miles away using that scale. So you can see why this doesn't quite capture that. Now, what this means actually is that given the actual size of nuclei, the neutron, on average, will travel 3.5 centimeters before it encounters another nucleus to cause fission. However, when we actually make the measurements, it turns out to be even bigger. So for the two fuels, for uranium-235, the actual average path before there's another collision is 17 centimeters, about 6.5 inches, and for plutonium, it's 5.5. And you may say, well, what was wrong with the prior picture? The answer is nothing was wrong with it. What's happening is, basically, the neutron will collide for U-235 4 times off of a nucleus before it finally causes fission. So imagine you had a frictionless pool table. It would be as if the ball almost went into the hole, but it bounced out, and it did that 4 times before finally sinking in the hole. And for plutonium, it does it 3 times before finally being absorbed and creating fission. So now we can understand the concept of critical mass and what it means and doesn't mean. Imagine you had a piece of aluminum a piece of uranium like foil, like this, and we had not just a little piece, but a piece covering this whole room or covering the entire state of California. You could have tons and tons of the uranium, but if that's the shape it's in, you would never have a sustained chain reaction, because almost every neutron that was emitted when a fission occurred would fly out of the foil. It would be extremely unlikely that it would fly in the direction of the foil, and even if it did, the subsequent fission would result in neutrons flying out. So you would never have a chain reaction if you just had a flat foil. To have a chain reaction, you want to maximize the volume relative to area. You want a sphere. But if the sphere is too small, again, you won't have sufficient size for a neutron to go and hit a nucleus. Most of the neutrons will just fly out of the sphere. So hence the concept of critical size and critical mass. For uranium-235, you need, at a minimum, a sphere 17 centimeters in diameter, which is 52 kilograms, almost over 100 pounds. And for plutonium-239, you need a sphere 10 centimeters, you need 10 kilograms. It's not that, supposing you had a sphere of only 3 kilograms rather than 52. If you remember, I said 1 kilogram is equivalent to something like 3.4 million tons of TNT if you had an explosion. So 3 kilograms of uranium is equivalent to 10 million tons of TNT. 10 million kilograms of TNT. Basically, that's equivalent to the bomb that destroyed Hiroshima. So it's not that 3 kilograms isn't enough to release an enormous amount of energy. It is. It's that it's small enough that most of the neutrons created in a nuclear fission would fly out, and you'd never have a chain reaction. So the minimum volume and the minimum critical mass is what you need to have a chain reaction. Now let's look 2 more features of this. How do you make a bomb? Well, you don't want to start out with a critical mass. You'll blow yourself up. So you have to join 2 pieces, 2 subcritical masses. One way of doing it is to fire like a gun, one piece into the other. That's called the shotgun method. The other, much, much more difficult method is to compress the mass that you have. By compressing it, you're increasing the density. If you work out the math, you can go from subcriticality to criticality. But it's very, very difficult to figure out how to do that. Two more slides, and then we'll discuss how do you make the material. What's the time between, we said that the actual fission process took less than a trillionth of a second, given that for uranium, the neutron needs to travel on average 17 centimeters, almost 6.5 inches before it hits another neutron. How long does it take to do it? Well, because the neutron is traveling at almost 5% the speed of light, it takes 100 millionth of a second. And this has very interesting consequences. Let's look at what happens after 80 generations. So let's assume every generation the number of fissions doubles. So after 80 generations, the cumulative number of fissions would be 2 to the 81th minus 1. And it turns out that's exactly or roughly equal to the number of nuclei in a kilogram of uranium-235. I didn't figure this out. This was actually figured out, and it was in the lectures I'll describe that were given at Los Alamos explaining about how to make a bomb. So after 80 generations, 0.8 millionth of a second, the number of nuclei that will have undergone fission is equal to the number of nuclei in a kilogram of uranium-235. Why do we care about that? Well, if you actually look at the amount of energy that will be released, each one is a tiny amount of energy, but when you have that many nuclei undergoing fission, the cumulative energy is so much that even though the minimum critical mass was 52 kilograms, and this is only 1 kilogram, less than 2% of this has undergone fission, the temperature will now be tens of millions of degrees Kelvin, as hot as the center of the sun, and the pressure will be extremely high. In other words, after 0.8 millionth of a second, you no longer have uranium metal, you have a gas, extremely hot gas, which is expanding. Why would that be a problem if you were making a bomb? Well, if the extremely hot gas is expanding, it means the nuclei are rapidly flying apart. The nuclei of all the atoms in the gas are flying apart, and it will end the chain reaction because the nuclei to hit are rapidly moving far away from each other. So how can we control or limit this expansion of the gas? Could we enclose the uranium in some kind of high-strength steel? That would be silly because everything is going to turn to gas. Nothing is going to be a solid at that temperature. But what was figured out is there is something to do called a tamper. So if the blue is the uranium, the fissionable material, and you surround it by a tamper, the hope is you can slow down the process. How do you slow it down? Not by having something that's solid that's going to stop the expansion of the gas, by having something that's very dense. So the tamper will be made of tungsten, it could be made of gold, which would be pretty expensive, or depleted uranium. All of them have a density about 19 times that of water. These are the densest materials on Earth. And it's tungsten that was used in the bomb on Hiroshima and depleted uranium used in the plutonium bomb that was tested at the Trinity site and used at Nagasaki. And the hope is that it increases the energy released in the bomb, it increases the efficiency by slowing down the expansion. Simply having this very large amount of massive material, it'll also turn to gas, but it's almost like if there was this huge crowd and you had running out of a room and you put doors on a frictionless hinge, so the doors could easily be opened if you push on it, but the more massive the doors are, the longer it takes to push them open. And if you can just prevent the expansion of the gas by 100 millionth of a second, you double the amount of energy released in the fission process. So that was the intention. And if the tamper is made of uranium, even the ordinary uranium-238, it won't undergo a chain reaction, but it's fissionable. And so you get more bang for your buck if that green stuff, this heavy material, is made of uranium-238 because the extra neutrons that are released can cause fission in it, not a chain reaction, but fission, and you get more energy. Okay, that's the theory. Now, here's the interesting thing. Robert Serber was a protege, then a friend, associate of Oppenheimer. When everyone met at Los Alamos in 1943, everything I've just described to you and more was understood. Serber gave a series of lectures, 5 lectures on everything I just described, but in much more detail. They were put together in a book called the Los Alamos Primer that was required reading for all of the scientific staff that joined Los Alamos. Serber eventually went to Columbia. He was a professor I had when I was a graduate student in physics. So the first year I took quantum mechanics, he taught the quantum mechanics course. And he was one of a number of people who either I sat in on lectures or courses or attended lectures they gave, who did important work at Los Alamos. So I have some indirect connection because I knew some of the people who worked there. So you may wonder, well, if all of this was known before anyone even came to Los Alamos, how did they even know this? And then what work needed to be done at Los Alamos? So in 1939, 2 expatriates, Jewish expatriates who had fled Europe, were in England, and Rudolf Perls and Otto Frisch, they were given the assignment to look into the feasibility of a bomb, and they created a very important and influential report in 1940 called the Fritz-Perl Report. And when Oppenheimer and Serber in 1942, so kind of a year or two later, took that report and expanded the theory underlying it. And then they held a summer conference, like we have a summer conference, but they had people like Hans Bethe and Edward Teller and a number of Nobel laureates to review the work they did. And at the end of this, they concluded, yes, we really understand nuclear fission. In fact, Serber reports that the attitude of the group at the end of that summer study was, everyone seemed to be saying, well, that's all settled. Let's talk about something interesting. So if that's the case, what was the challenge in building the bomb? What were the greatest theoretical and engineering challenges in building the bomb if the theory was so well understood? And if the theory was so well understood, it would have been understood by physicists in Germany and Russia and Japan. There were very smart people still in each of those countries. So why didn't Germany, Russia, or Japan develop nuclear weapons during World War II if the theory was that easy to understand? So I'll answer the first question, what were the greatest challenges, in my talk, and you could ask me about the second question during the question period. So how do we make a bomb then? Well, the management of the process, before it was given to the Army, it was under the control of civilians. Ask me in the question period who they are, but these, particularly the first 2 men, Vannevar Bush and James Conant, played an extraordinarily important role in all of the scientific work that was done with military application during the Second World War. And now let's jump to 1942, May 1942. So the US entered the Second World War in December of 1941, 6 months earlier, and by now there was a very strong focus on we have to make a bomb. Everyone thought and had reason to believe Germany was working on an atomic bomb, and the US was in a rush to create a bomb before Germany did. And James Conant had to make a very important decision. And the decision was, how do we create the fuel to make a bomb? This was an essential requirement, obviously. And there were 2 choices. Do you build a uranium bomb? And if you do, how do you separate out uranium-235, the fissionable material, from the 99.3% of uranium that isn't fissible? there were 3 possible methods, but none of this had been actually developed and worked in a production process. Or do we build a bomb with plutonium, and how do we create plutonium? We're going to need a nuclear reactor. There wasn't any nuclear reactor in existence. It hadn't been invented yet. And what are the potential ways of building a nuclear reactor? Do we use graphite to slow down the neutrons, or heavy water? So the context was we were in a war, and it was viewed that whichever country, the US or Germany, US/Britain versus Germany, whichever country built the atomic bomb first, that having the bomb would be used as blackmail to end the war. And so nothing less than civilization was at stake. And this was a literal life and death issue. But Conant was aware that there was uncertainty in any one of those choices. Will it work? How much time it was needed? So he had to make a decision about what path to follow. And what he decided was to proceed in parallel on all 5 paths. And the reason was, his decision was, time is the essence. Time is the most important variable. I don't know enough to know which of these processes will work and will work the fastest. And I'm very worried if I pick 3 of the 5, I'll end up not having picked the process that will result in the quickest way of making the bomb, and that could result in Germany making a bomb first. So it was a very good decision, and even wiser than he realized for reasons we'll say. Now you may think, oh, well, this is easy, he isn't undergoing a cost-benefit analysis. But even if you did that, and that wasn't the appropriate criteria, even if you thought about the cost of this, in today's dollars, the cost of the Second World War was about $4 trillion in today's currency. That's $1 trillion a year, over $80 billion a month. The cost of the Manhattan Project was roughly $2 billion, which is about $34 billion in today's money. So the cost of the Manhattan Project relative to the cost of World War II to the United States was 2 weeks worth of costs. At a minimum, using the bomb in Japan ended the war much sooner than 2 weeks. So even if you just did like a crude analysis of cost-benefit, it was worth every penny, but much more important, it saved potentially hundreds of thousands of American lives. And that's the moral justification for having built and used the bomb. It saved American lives. Once this decision was made, it was realized that the main difficulty is an engineering difficulty, and the project was assigned to the US Army because they had a lot of experience managing large-scale engineering projects. And in September, General Groves was appointed as the leader of the Manhattan Project. As you can see from his picture, he has little epaulets, meaning he's part of the Army Corps of Engineers. He was a very, very smart man, very hard worker, driven, decisive, arrogant, but extremely good at managing projects. He had just come from building the Pentagon, and he got it built, in time, under cost. So he was an extremely good project manager. And when he took over, he began making very quick decisions that had been kind of hanging there. There were 4 centers where the Manhattan Project was spread out all over the country, so there were many centers that did work, but the 4 primary ones was one that was formed even before Groves was appointed. It was the metallurgical labs in Chicago. What had happened was Arthur Compton, who was a Nobel laureate, but also one of the civilians managing this, made a decision that all work on nuclear reactors and all research on plutonium should be centralized in one place at the University of Chicago. So Enrico Fermi and his team went from Columbia to Chicago. Eugene Wigner, who was at Princeton, went to Chicago. People who were working in the radiation lab at Berkeley went to Chicago, and we'll return to Chicago. So all the research on nuclear reactors and plutonium was centralized there. when Groves was appointed, he bought land, a huge amount of land in Tennessee at Oak Ridge, and that's where the facilities to separate U-235 from U-238 were constructed, and it was also where a prototype nuclear reactor was built to manufacture plutonium. I have two Nobel laureate scientists up there. Ernest Lawrence was responsible, who was a Nobel laureate at Berkeley who invented the cyclotron, was responsible for one of the methods, which we'll discuss in a few pages, of separating U-235 from U-238. And Harold Urey, who was a chemist at Columbia, who also won a Nobel Prize, was responsible for the other two methods. By the way, Compton and Fermi were both Nobel laureates. So you can see, the reason I mentioned their Nobel Prize, like every Nobel laureate in the States in the sciences were put on this worked on this project, and as well as many people who eventually won the Nobel Prize. So like the smartest, the most accomplished scientists in the United States, and many other scientists who never won Nobel Prizes but were brilliant, worked on this project. In Hanford, Washington, was selected for the site to create plutonium, and in both Oak Ridge and Hanford, the sites were selected because they were near rivers, which they needed for cooling the facilities they were creating, and they were near enormous sources of electricity, the TVA in Tennessee and some large dams on the Columbia River in Washington, so that both of them had like an almost unlimited sources of energy. And finally, the fourth place pick, which you're all familiar with, was Los Alamos, which Groves picked with Oppenheimer. Oppenheimer was very familiar with New Mexico and that area. And the purpose of Los Alamos was to design the bomb. So you had these three centers: design the bomb, create U-235, create or produce plutonium-239. Let's see how this worked. So how are they going to separate out U-235 from U-238 atom by atom? They're identical chemically. They only differ in 3 neutrons, so they have a very slight difference in mass. They have identical chemical properties, and their mass differs by a slight amount. U-235 has 98.3% of the mass of U-239. So you may wonder, well, maybe you hire a lot of graduate students, and atom by atom, you put this on a scale. No, that's not how you do it. You take into account their inertial mass, because this is how they were identified as separate isotopes. This is this is not a good view, but bottoms up. So imagine you have 2 large magnets on the side and you're looking at the bottom up. You have 2 large magnets, and between them there's an emitter and a detector. And so there's 2 large magnets on either side of that piece of paper. And what occurs is you take any material, let's say it's gold or tin or copper. If you chemically reduce it to a pure element and you then put it in the emitter, and you have within the emitter a process for melting the material to a gas, ionizing it, and then shooting that gas through electron potential, the ionized atoms will come out very fast, but because they're ionized, they have a charge, and because they're moving in a magnetic field, they'll undergo different forces, magnetic forces, and the light atoms will be bent much more than the heavier atoms. And this is actually how a mass spectrometer works. It was invented initially by someone in Ernest Rutherford's lab, and it was how scientists discovered eventually that there were 92 elements, but 339 naturally occurring isotopes, because for every element they could count. Well, how many separate beams are created? Each of those beams has a different mass. So it took a long time, but that's how these were discovered. The problem is we're talking about, atom by atom. So how do you create a large amount of this? So one of the methods that was worked on was using this, but on a much, much larger scale. they turned to Ernest Lawrence, who invented the cyclotron and who at Berkeley had built bigger and bigger, more powerful cyclotrons. So he basically took one of his old cyclotrons and converted it into a method on a very large scale for separating out the two isotopes. And they called it a calutron, an abbreviation for California University cyclotron. So essentially, it's a mass spectrometer on a giant scale where, let's say, the lighter atom in this case will be the uranium atoms made of 235. They'll have a collector. And this will be really crude, really messy, but this is what they used. And so this is what the emitter looked like. There are two scientists and two technicians on an advanced emitter. So that little box there now has 4 separate devices that are emitting and you can see how large it is. And on the upper right, we see what one unit is. So each of these is about as big as a man. Here's an example. They had it's called a racetrack. They had 100 units. And altogether, they built at Oak Ridge about 1,000 of these units. Now, each unit required a separate giant magnet, and each of those magnets required an enormous amount of conducting wire to conduct a current. They realized that so much copper would be needed that it would conflict with other uses of copper for the war. Copper was needed for battleships and submarines, for airplanes, for tanks, for jeeps, for communications, for radar. And they decided, well, what is another metal that conducts electricity very well? Silver. So they went to the US Treasury and said, we'd like to borrow, and they told them how many tons of silver. And this was a very interesting conversation. It was an aide to General Groves. He met with this elderly man at the Department of Secretary and said, we would like to borrow X amount of tons of silver. And the undersecretary said, how many troy ounces is that? And Colonel who spoke to him said, I don't know, what does it matter? We need, tens of tons of silver. And the undersecretary said, young man, in the Treasury Department, we measure the weight of silver in units of troy ounces. Well, what they needed was something like 430 million troy ounces. They needed 14,700 tons of silver, almost 30 million pounds of silver to just create the wiring to separate out the two isotopes. So that, you could see, pretty big project. This was one method, but it wasn't a very good method. If you saw the film Oppenheimer, you saw that from almost the time the lab opened, Robert Oppenheimer had 2 bowls, the amount of uranium we have and the amount of plutonium we have, and he kept dropping marbles in the bowl from the start. In fact, this is actually from the amount of, this is like a real data that they kept track of. So you can see they actually didn't start getting any material amount of silver material amount of U-235 until the last, a few months before the bomb was dropped. And when they dropped the bomb on Hiroshima that used uranium, they only had enough uranium for one bomb. It took more time before the processes fully worked. This was a very difficult thing to get to work correctly. And in fact, ultimately, remember I said that more than James Conant realized, having many parallel projects having many projects in parallel worked well. That's actually what occurred. They actually, used every one of the processes, because it took a long time to perfect each one of them, so they used them sequentially to go from 0.7% to 90% uranium to make the bomb that was dropped on Hiroshima. The second big process, and the process that ultimately was used in the Cold War, is called gaseous diffusion. So imagine you have a steel tank and you have gas in it under a lot of pressure. in the 19th century, a scientist observed that the rate at which gases will diffuse through a semiporous barrier. Semiporous barrier is a piece of material that has microscopic holes. I mean, really microscopic, very small holes, so that the gas molecules will bounce around and exit. And it's found that the rate of diffusion, the rate at which gas molecules can leak out of this steel tank, is inversely proportional to the square root of the mass. You may say, where does the square root of mass come from? This was all explained eventually by kinetic theory. And if you remember from basic physics, the kinetic energy of any object in motion classically is 1/2 mv squared. So what this is really saying that at a given temperature, where all the molecules have the same average kinetic energy, the rate of diffusion is proportional to the speed. Light molecules will have a higher speed, they'll diffuse faster. So imagine you had a container that had, first we had two separate containers, one with hydrogen and one with oxygen. And that's roughly their mass in units of atomic mass units. This says, apply the formula, oxygen is going to diffuse at 1/4 the rate of hydrogen. Why is that relevant to our discussion? Well, imagine now you had a gas that was 50% hydrogen, 50% oxygen. Then initially, the molecules will come out 4 molecules of hydrogen for every molecule of oxygen. The oxygen is coming out 4 times slower. That means, even though they're 50-50, when they come out, they're 80% hydrogen, 20% oxygen. So the thought was, well, this will work for these light gases. Let's try this for uranium. And so the idea was, we have a gas not of 2 different elements, but of one element with slightly different masses. And initially, we take uranium, it's only 0.7% concentration of U-235. If we use this device and we take into account the ratio, we'll increase that ratio, not by very much, by 0.006%. So the first stage, you'll only get a very slight enhancement. And if you assign this to this could be an assignment to maybe an upper, junior, senior undergraduate to actually build the process. A quick word, this would be one stage. You don't want to throw out the stage that wasn't enhanced because it still has a lot of U-235 molecules. What you do is you feed it into a second stage, a second process, enhance, not enhanced. Well, not enhance and enhance gets you back to the start, so you have a feedback loop. And so you end up with 2 stages. You require your initial process and one above and one below. If you go to 4 stages, you require 9 processes. But 4 stages, you're still getting very little enhancement, but a little bit. And so you could assign this to a smart undergraduate, and he or she could work out the mathematics of how many stages would you need, and let's do the calculation correctly so we're not creating U-235 molecules out of nothing and they're not disappearing. You could give this assignment and someone could figure out, an undergraduate could figure out, how many stages, if this were the design, would you need to get 90% or 80% pure U-235? There's a problem though. Nothing I just described would actually work. And the reason why is a really important issue. It explains how you can't blindly apply principles without taking reality into account. So we've omitted that formula, which is true, is a general formula that omits many measurements, like all abstractions. So what measurements were omitted? Well, one measurement was, what temperature does uranium become gaseous? Uranium becomes gaseous at 75,000 degrees Fahrenheit. Steel melts at 2,500 degrees Fahrenheit. So this is going to be a problem. How are we possibly going to build a process that isn't going to melt? So the answer was, scientists had already figured out that there was a way of taking uranium, adding 6 fluorine atoms to the uranium atom, and you create a molecule called uranium hexafluoride, or hex for short, that because of the different chemical composition, now you have 6 fluorine atoms attached to the uranium atom, a new molecule. It becomes a gas at a much lower temperature. And so you might say, okay, now we still need heaters and compressors. That's what these devices are, but it looks like this might work, except this gas is toxic, highly radioactive, highly corrosive and radioactive. So the first challenge they had was they couldn't figure out how to design a porous barrier that would work. This material with tiny holes. What worked for oxygen and hydrogen and very light elements didn't work when you had this very heavy molecule at a very high temperature. And it took a very long time before they finally figured out how to create that. Second problem, corrosion. They discovered that this ate away at all the material of whatever material they were using in the pipes and in the chambers, and they had to line it all with stainless steel in order to prevent corrosion. Third problem is that the uranium hexafluoride, ate away at the rubber or the sealants in all of the vacuum pressure devices, which meant it would eventually leak out and kill people, as well as contaminate the process. So they needed a material that was resistant to this, that wouldn't corrode. And it turned out a few years earlier, someone at DuPont, who doing research on refrigerants, discovered a kind of gook accidentally created. Did a chemical analysis. Its chemical name is polytetrafluoroethylene, PTFE, and it turns out PTFE had remarkable properties, but it had no use, so it sat on the shelf until there was a need for it, and it turned out to be the ideal sealant that enabled this gas diffusion process to work. After the Second World War, PTFE began to be used commercially, and you probably have it in your home. It's called Teflon. The first actual large-scale use of Teflon was for this purpose. So this just illustrates the challenge of taking an abstract formula, which is perfectly valid, still works, but reintroducing the measurements and taking all of the details that had to be solved, all the physical facts of reality that had to be dealt with to actually create this process. Now, this was eventually used, and it was used all through the Cold War. So for many decades, this was the principal way of separating out these two isotopes. So try to picture how big you think the plant was. Do you think it was as big as this room, or big as the auditorium next door? This is the plant that was built. When it was built, it was the largest building in the world. 4 stories, half a mile long, 1/10 of a mile wide. I mean, these are automobiles here. So this was a gargantuan, and they eventually built 3 of these. But it took a while not only to build the building, but they kept refining the method. So that's why at the time of Hiroshima, they only had enough uranium for 1 bomb. But during the entire Cold War period, this was the principal way of separating out U-235 from U-239. Now, the principal method used is, of course, centrifuge. And that's why it's a really big deal when Iran has centrifuges, because you have to do this separation if you're going to create a bomb. So you can see, really big project. Here's an example of how big each of these chambers, diffusion chambers, are. So you can see over here, there's a switch. So assume a person is about this tall. So these were enormous, and they had 3,000 of these, 400 miles. How do you manufacture plutonium? Well, sorry, I'll say this really quickly. There are 2 common forms of carbon. Again, this is the issue of isotopes, carbon-12, carbon-13. But there's also a third kind you've all heard of called carbon-14, which has a half-life of about 6,000 years, meaning it undergoes natural radioactive decay. And that's relevant for what we're about to discuss, because when carbon-14 undergoes this decay, it becomes nitrogen-14. You say, how can that be possible? Because in the nucleus, when this decay process occurs, a neutron becomes a proton and emits an electron and a neutrino. Let's ignore the electron and the neutrino. You can ask me more about it in the question period. For our purposes, what we want to focus on is this is a way that, and this was discovered in the early part of the 20th century, an element gets transmuted to the next element in the periodic table. And it was, this process was first explained by Enrico Fermi, who was unusual in that he was both a theoretician and an experimenter. And then once he explained it, he began the process of firing neutrons into almost every element in the periodic table to observe if he could artificially induce this transformation. It was this process ultimately that led to the discovery at Berkeley lab of two transuranic elements, neptunium, which has 93 protons and has no function other than to create, the only practical use of value it has is it's a way of creating plutonium, which is useful as a fuel. So how does this work? For our purposes, we can think of it as follows. We have a slow neutron hitting U-238. That's the non-fissible form of uranium, the most common form, and it creates a nucleus with one extra neutron, U-239. It was discovered that after about 23 minutes, U-239 decays by this process called beta decay into a new element, neptunium. It has one more proton and one less neutron. So neptunium-239, and it emits an electron and neutron. And then after 2.5 days, this decays into plutonium-239. So we have two transformations all occurring within less than 3 days of uranium into plutonium. And therefore, this is how plutonium is made. So in order to make plutonium, you need a process that is going to provide you with a very large source of neutrons. It'll have to be much bigger than the tabletop experiment that Fermi did. It will have to be much bigger than even the cyclotron that was used in Berkeley. In fact, you need a nuclear reactor, but none existed, but fortunately, Enrico Fermi was inventing one. And once it was invented, once you actually could create plutonium, you needed a way of chemically, this was much easier than the other type of separation, separate plutonium from uranium. And the man who discovered plutonium, Glenn Seaberg, who was a brilliant chemist at Berkeley, he also figured out a way of how to separate that. So what did Fermi do? Let's say this very quickly. He built the first reactor, and he did it, I'm going to have to, let me skip a lot just to say that first picture I showed you when I said the area, relative area was 1 in 100 million, therefore we only looked at the geometric size. It turns out that's very correct way of looking at things when you have very fast neutrons. But when you have slow neutrons, their quantum mechanical properties enter. The fact that they have wave-life properties. And slow neutrons that are traveling 1/10,000th have 1,000 times more likelihood of being absorbed by the uranium nucleus than fast neutrons. So Fermi, who discovered all of this, used slow neutrons in his experiment because he wanted to take U-235. The two were mixed. He had no means of having pure U-235, but he was going to use this mixture, natural uranium, which is a mixture of the two, use slow neutrons to create nuclear fission with the fraction of the atoms in natural uranium that were 235. How did he do this? Well, there was no manual to follow. He figured this out, working with Leo Szilard, who was another physicist, and several other physicists at Columbia. So the first 2 years, this was all done at Columbia. He had a source of neutron, natural uranium, which was a mixture of the two, graphite, which slowed down the neutrons to very slow motion so they could be controlled better, instruments to measure the nuclear flux, and cadmium, which absorbed neutrons so that he could he had a safety way of ending the reaction if it became a chain reaction. And this is what he did. He took graphite brick, drilled a hole in it, created a ball of uranium and put it in there, and then created a cubic lattice of uranium embedded in graphite. And it took a lot of steps to even figure out to do this. So every step of the way, he did exhaustive experiments and knew exactly the effect of everything. I could spend just half an hour telling you how he got to that first or second stage. But let me just mention one interesting thing. When he built his first large lattice at Columbia, he wrote in his lab book, disappointed with the results because he was expecting more neutrons to be generated than were actually. So he and another scientist, Leo Szilard, visited the manufacturer and had a long discussion with the manufacturer, which included a physicist who worked at the manufacturer, and they discovered that the uranium they were getting, which was as pure as it was, it was called pure uranium, actually had various elements that were contaminating it. They just were introduced in the process of making it, including boron, which absorbs neutrons at a very, very fast rate. So Fermi said, well, we need much purer graphite. Can you produce graphite that has, let's say, less than 1 part in a million boron? And the answer was yes. Once that was created, this was the perfect tool to use in building a reactor. Interestingly, in Germany, Heisenberg, who was in charge of the German process, did exactly the same experiment and concluded graphite is not useful. Because he never asked, why is this graphite not useful? And so never spoke to a manufacturer in Germany. And so Germans were looking to use what's called heavy water to slow neutrons, and the Allies kept destroying the sources of heavy water. So once in December 1942, this all moved to Chicago. Fermi built what was called Chicago Pile 1, but this was built after many, many experiments. And this was the first sustained nuclear chain reaction ever created. And it was done with complete certainty by Fermi that everything was going to work, and it did, exactly as he anticipated. But to give you a sense of the size, it involved, 56 tons of uranium, 400 tons of graphite. There's no moving parts. All they're trying to do is see if they can create a sustained chain reaction. The reason they needed so much material is, remember, only 0.7% of the uranium is actually U-235, and they had no way of separating out the two at this time. And this was a replica of what you could see, it's 25 feet tall, 20 feet wide. This is a replica that's now in a museum, and Fermi and the other scientists were on the upper right. It worked. And so this is how he created the first chain reaction. And then they had to build a plant. They built a plant in Hanford, 3 plants. This is only one of the 3. Essentially what they did is they did what Fermi did in Chicago on a massive scale, and they had tubes. They had like hollow cylinders. They put tubes filled with uranium and baked them. And that baking, just exposing the uranium to the neutron flux, converted some of it into converted some of it into plutonium. So that's how they made plutonium. They used uranium to create a chain reaction to produce neutrons to irradiate U-238 to create plutonium. And that's how they made plutonium. Last thing, I mentioned that the subpieces needed to be, there were 2 ways of joining the subpieces. One was to use a gun method, and that worked fine for uranium. In fact, they never tested the uranium bomb. They were so certain that the bomb that was dropped on Hiroshima would work that they never had a test site of it, because it was a very simple design. But this doesn't work with plutonium, because they discovered that in the process of manufacturing plutonium, inevitably, another isotope of plutonium was created that underwent self-nuclear fission and released neutrons. And therefore, they realized that if they used the manufactured plutonium by this method, it would very likely, it would be uncontrollable. You would have either, it would fizzle. It would, without even intending it, you'd start a chain reaction and there'd be an explosion, not a big one equivalent to an atomic bomb explosion, but this method of joining the subcritical masses to a critical mass couldn't work with plutonium. And so they had to come up with another method. And the other method they looked at was an implosion method. The idea was you apply force uniformly. Imagine this is hollow. You have the blue is the plutonium, and the green is the tamper, and you uniformly compress it. Sounds easy to do. If you could do that, you would then have a critical mass and an explosion. But no matter how much they tried, they couldn't figure out how to do it. And the solution came from John von Neumann, asked me about in the question period. He's a brilliant mathematician. He figured out, that what one was needed to do was create an explosive lens using two different explosive chemicals so that you trigger an explosion. You first have a convex wave of explosive, and then when it goes through it gets converted to a converging. Here's what it looks like. So imagine here, you detonate, the explosion occurs. This is a chemical explosion. The purpose is to squeeze the material so that you'll have a nuclear explosion. And you can see how it's shaping the way each of the separate lenses, in each of the lenses, the explosion is getting shaped so that it ends up being a converging explosion. There's compression, and then you have an explosion. And that worked. That's what was used at Trinity and at Nagasaki. And I'm leaving out a ton. There was lots of experiments, lots of design work, lots of work on the electronics, but the key idea was from von Neumann. This was 2 dimensions. This is what it looks in 3 dimensions, and this is what it looks like in an actual bomb. So here now we have the 2 bombs, and the point of this slide was to say there's a benevolent universe because it's extremely difficult to create a nuclear bomb. If it were easy, we probably wouldn't be here because some madmen would have already built it and blown us up. So whether you look at U-235 or plutonium-39, at the difficulty of extracting them or of designing the bomb, any combination you end up with is extremely difficult. We don't have to go through this. This is all the detail about how well each of the bombs work. I'll just say one thing. The bomb that was dropped over Hiroshima, only less than 2% of the U-235 actually fissioned, just because of the process used. It still was a powerful explosion, but the implosion bomb with plutonium is much more efficient. So basically, the shotgun approach was not used anymore. Sorry I went so quickly, but there was a lot to cover. So all of these achievements were due to great scientists. I haven't said a word about Oppenheimer yet. He played a very important role at Los Alamos as an integrator, and you can ask me more about his role during the question period. But for the people I've shown you to the left of him are the ones that solve the major problems. And you could also ask me about the people who, this is the 3 people I mentioned as managers of the overall project. Here's a picture of them in 1945. And then 25 years later, there's some former president whose name I forgot. There's Glenn Seaberg, who's then chairman of the AE's Atomic Energy Committee, and President Nixon giving an award in the White House to these 3 men for the work they did. So, one last thing. This book I've read this like 2 or 3 times. This has a wealth of information. If you want to learn about the bomb, read this. And this book by Serber is also very valuable. So sorry I went way, way over the time limit, but now I'll answer questions. That's it for the lecture. Do you have any questions?
I just want to, is this working? Can you hear me?
Yes, I can.
All I want to say is this has been the loudest and clearest speech that I have had at this conference.
Thank you.
Do you all agree? It's terrific. And the only question I have is for fun. Did they actually get all the silver from the Treasury?
They returned all but like some X%. So it all got melted down, made into wires, and at the end of the process, virtually all of it was returned. There was very, very little loss.
Oh, interesting. Thank you.
Can I have like an explanation about how the relationship between matter and energy in the atomic level, just to understand how energy is in matter? Okay.
Yes, you can, but we could discuss it offline because it wasn't relevant for my talk. Actually, the energy of the nuclear fission that I described is once the nucleus splits, you have two daughter nuclei that have both positive charge. And because of that, there's enormous force pushing them apart. And as they travel apart with enormous speed, they heat the matter around them. And so almost all of the energy in nuclear fission is created just by this repulsive electrical force. We just don't have time. We could talk afterwards about mass and energy, and it's actually important to understand some of the observations that underlie the discovery of fission, but it isn't important. You don't need to understand that to understand the fission process.
Do you think that it's possible to have nuclear power that is safe and practical, and if so, how?
I'm not a nuclear engineer. My PhD was in experimental particle physics, but from everything I understand, the answer is yes, but I'm not there are people here who are nuclear engineers or work in that field, fission or fusion. I don't. So I think it's an enormous unused source of energy. I think in France, something like 30 or 50% maybe higher, of all of their electrical power used to be from nuclear fission. There was no problem. So yeah, it's an enormous misjustice, or we should be making much more use of nuclear fission until nuclear fusion comes on board. But I don't know enough to say beyond that.
Would you please discuss how Dr. Oppenheimer happened as an integrator of the project, but also how his name became the dominant one under the discussion of the atomic bomb's development?
I can't hear I apologize, I couldn't hear the last part of your question.
As well as, now it's working well. Both Dr. Oppenheimer's role as one of the main integrators of the development, but also how his name became the main name used throughout the discussion of the atomic development project, especially with not only the biopic, but also Times article labeling him as the father of the atomic bomb and so on.
He was a genius. He was extremely smart, and the role he played was primarily as an integrator. And he actually surprised people. So I have quotes from both Edward Teller and Hans Bethe about him. So this is what Teller said. So this is from Richard Rowe's book. Robert Oppenheimer oversaw all of the activity of the Manhattan Project with self-evident competence and an outward composure that almost everyone came to depend on. Then, quote, this is from Teller, quote, Oppenheimer was probably the best lab director I ever have seen, Teller reports, because of the great mobility of his mind, because of his successful effort to know about practically everything important invented in the lab, and also because of his unusual psychological insight into other people, which, in the company of the physicists, was very exceptional. He knew and understood everything that went on in the lab. Bethe, this is Hans Bethe now, Bethe concurs. Whether it was chemistry or theoretical physics or machine shop, he could keep it all in his head and coordinate it. It was also clear at Los Alamos that he was intellectually superior to us all. Then Beta continues. He understood immediately when he heard anything and fitted it into the general scheme of things and drew the right conclusions. There was just nobody else in that lab who even came close to him in his knowledge. There was also human warmth as well. Everyone certainly had the impression that Oppenheimer cared what each particular person was doing. In talking to someone, he made it clear that that person's work was important for the success of the whole project. I don't remember any occasion in Los Alamos in which he was nasty to anyone, whereas before and after the war, he often was. At Los Alamos, he did not make anyone feel inferior to anyone. So he was extreme. It was like this was the role he was born into. He was very, very good at both mentally integrating, coordinating everything into this large picture, motivating people, making good decisions. But that was his role here, primarily as a manager. As I said, the theory, he and others had worked out the theory beforehand. And so the problem, the challenge wasn't, wow, we need a genius to figure out how to do this. We need a genius to manage this very complex project that is being done under enormous pressure in as short a time as possible. And that's what he did well.
Thank you very much.
I'm curious to know your perspective on the movie Oppenheimer. Anything in particular that you thought they got right or did well, or the opposite? That didn't?
I'll only say briefly, I enjoyed the film, but it contained an enormous number of details that I recognized from reading the book almost 3 times and other research I did. So there were lots of little things that I could say, here's a chapter in this book on this little thing. But I don't think the film at all conveyed what I tried to convey to you, what the actual challenges were. The film made it seem like, well, there's some of these really smart people, and it showed some scenes of things being blown up in tests, but you had no clue what the actual challenges were, where those challenges were, or who solved them. So one thing I left out, an enormous source of solving these problems was the US industry. So when I said the Army was in charge, they were coordinating like the building of these plants, but people like firms like DuPont and other American industrial firms were given the contracts to build the process to produce plutonium, or to build the process to separate out U-235 to U-38. So this was an enormous for most part, this was an enormous engineering, applied industry project. The theory was, for the most part, other than the implosion, all worked out. And that's nothing the film didn't capture.
Thank you.
Thank you for the talk. It was, all scientific, your talk. So may you author, ask a political question regarding the atom bomb?
Sorry, I didn't understand your question.
Can I ask a political question regarding the atom bomb?
I still can't. Maybe I apologize. My hearing isn't great.
He's not speaking up.
Okay, nice. Can I ask a political question regarding the atom bomb?
You can ask it. Let me see if I can answer it.
Yeah, I'm going to ask it anyway. Yeah, do you think they keep the war in relatively peace these last 80 years? Or?
That's a very good question. In fact, even many of the people, the question was, did the atomic bomb keep the peace? And I think in a sense it did. I mentioned this document called the Pearl-Fritz memo, which was written in 1940. So this was the first memo that said, here, an atomic bomb is feasible. Here, they underestimated the difficulty of actually creating the uranium. The plutonium hadn't been discovered yet, but it was a remarkable document. And one of the things they concluded, this was in 1940, it was 1939 it was written, published in 1940, it's available. If you had 2 opposing sides, at that time it would have been Germany and Britain, the US wasn't in the war yet, that both possessed atomic weapons, they realized there'd be a stalemate, that the consequence of either side using it would be to devastate their opponent, and there'd be, they came up with the concept of mutually assured destruction. And we were in that state during the Cold War, that neither side used nuclear weapons because they knew the other side could also, and it would be too horrific a consequence. So in that sense, what we've had is a lot of local conflicts rather than another world war. So, Peter or others might have a different, more informed view, but from my perspective, I think having such horrific weapons did prevent another world war from occurring, but we've had a lot of smaller wars instead. At least that's my understanding.
I didn't hear you mention Richard Feynman.
Correct, because he was a young man who didn't play a major role then. He was really, really young. So that's why I haven't mentioned him. He was one of many brilliant people who worked at Los Alamos, but he was like, one of the youngest people there. So he didn't make a material contribution, although he was a brilliant mind. And he was actually given major responsibility, but not anything that would show up on my presentation. You have to understand, let me just one example I didn't discuss. So they assigned Norman Ramsey, who most of you never heard of. He ended up winning a Nobel Prize for research in nuclear physics, so a brilliant man. What was his assignment? His assignment was to make sure that they selected the right airplane. They selected this newest B-29 Superfortress, and that it was fitted to carry both versions of the bomb, and also he worked on creating mock-ups of the bomb so that pilots like Paul Tibbets, who flew the Enola Gray that bombed Hiroshima, actually had a lot of practice flying those new planes with virtually mock-ups, same weight, same design. So they actually had a lot of practice dropping mock-ups of the bomb. And he worked on all aspects of that. And it was just one example of how Oppenheimer and Groves were able to recruit just the most brilliant people around, and they were willing to work on the most mundane tasks, like, this is not fun, but just because they wanted to make sure they had the bomb and they could use it to defeat first Germany and then Japan. So the project is, one of the things that's amazing to learn about the project is how many brilliant people contributed it to, every aspect of it. There's not a detail you can't think of that they had a brilliant person in charge of making sure this would work.
Yeah, you mentioned an experimental failure on the part of Heisenberg, and you also praised the management abilities of the American project managers. Were there any really significant management failures on the German side? And I'm also curious if you would be inclined to link them, if they do exist, to the varying socioeconomic systems, fascism and capitalism.
I think there were several problems. One of them was identified in the movie, just the fact that the Nazis were anti-Semitic, and they meant anti-Semitism not as we're opposed to some belief system, but crude racism. Anyone, like Niels Bohr's mother was Jewish. Niels Bohr wasn't religious. Well, he was a Jew. Hans Bethe's mother was Jewish, but Hans Bethe was brought up in the Lutheran church, but because his mother was Jewish, he was a Jew. So all of these scientists who had any Jewish background had to flee, and many scientists who just were opposed to the Nazis fled. So there was enormous brain drain from not just Germany, but Eastern Europe into the US. Most of the scientists who made major contributions were from immigrants who just were brilliant immigrants, cream of the crop, came here. And that was one reason. I'm not sure how enthusiastic Heisenberg or any of the Germans were. Heisenberg was a nationalist, but not anti-Semitic or Nazi. He, as well as Otto Hahn, who was this famous chemist, stayed in Germany for really bad reason. The reason was we want to preserve, quote unquote, German science, which Doesn't make any sense. I mean, science is universal. They didn't have to stay in Germany. They could have left, and when Germany was defeated, returned there to help rebuild the science. So that idea that, well, I also have a loyalty to my country and I have to stay here is obviously totally fallacious. But so I don't know how, if any of the competent scientists had any enthusiasm for doing what they did. They certainly didn't act with it as if, like the US scientists did, which they viewed it, this is life and death. We have to make sure we have a bomb before Germany did. From what I know, none of the German scientists acted that way. The ones that were competent that actually did any work on the bomb.
So, sorry, was it close, just yes or no?
No, the German got nowhere. They made the fundamental error Heisenberg made, so they were relying on heavy water, and the Allies made sure that the one major source in Norway was either bombed or they worked with the Norwegian underground to make sure it always blew up. And so the Germans never got the heavy water to even create a reactor to create self-sustaining nuclear chain reaction. So they got nowhere. They were not even close. But the Allies didn't know that. They had every reason to think that Germany would get to the bomb first, but they were nowhere. And after the war, the Soviets got the bomb only because they copied it, spies and thefts. Everything they did was a replica of the US. I think, again, there were brilliant scientists in Russia, but they had none of the industrial capacity to do what the US did. So everything they did was simply copying what they stole from the US.
Thanks, great talk.
While explaining how to make plutonium, you said that you had to have uranium, which would then turn into, what did you say?
Plutonium. So uranium played two roles. U-235 could be used to create a chain reaction, which would generate a lot of neutrons. Then U-238, a different isotope, absorbed the neutrons and got converted first to Neptunian and then plutonium. So that's how you created plutonium. You basically took U-238 and you put it in what's called a breeder reactor, which is simply generating lots of neutrons. You bake it until enough of the U-238 atoms are converted to plutonium, because the nucleus absorbs a neutron and then undergoes these two beta decay process. So it was very time consuming, and then they had to take the U-238 and they went to another lab where, behind shielding, using chemical processes, they extracted the plutonium. And all of that was figured out about how to do that extraction by Glenn Seaberg.
And you said that a neutron had to turn into a proton?
A neutron.
How exactly does that work?
This is called beta decay, and it's just part of nature. We could talk afterwards if we're both around, but it's just something that happens in nature. Under some contexts, a neutron will become a proton and emit an electron and a neutrino. The reason this can occur is the neutron and proton are not fundamental particles. They are made up of smaller things called quarks. And when you look at what happened, they're like fraternal twins. They're very similar, have the same mass, same size. They just differ like slightly in their composition. And the internal quarks, so at the quark, one kind of quark can turn into another through a process we won't discuss. And then that's where this electron and neutrino come from. And it's just part of nature that this transformation can occur. It's just reality that one kind of substance turns into another. And I think, I'll say it would be too long to explain why that can occur, but it does occur.
Okay, thank you.
Okay. Hi.
Beautiful talk, Evan.
Thank you.
Can you touch base on what type of instrumentation these scientists use? So how were scientists able to gauge atomic accuracy in an age devoid of modern computers? They
actually were very inventive. So the question is, what instrumentation was used? So let me just give one example. I described the implosion process, describing the work that John von Neumann did, brilliant mathematician. But there were many stages. They had to build and design the explosive lenses. They had to test it, all before they're not going to test it with actual plutonium and blow themselves up. So how did they test it? Someone had come up with a way, for example, of using radioactive material to put in to actually make the explosive material itself radioactive, so it emitted X-rays. They would take X-ray pictures as the explosion occurred, and they could monitor the density of the explosive material. It was called radioactive lanthanum. So they actually, you would say, how can you possibly measure whether you have a uniform compression? They made the explosive material itself radioactive. It emitted X-rays. They took photos of the X-rays, and if compression occurred, they would see if the compression occurred in a uniform way, they would see this when they measured the X-ray intensity. So they were very, very clever in coming up within the context of the times of like almost brilliant ways of measuring what they needed to measure to make sure they could make the bomb they made. So all of this was just like an incredible creative amount of work under enormous time pressure, which was done.